So let me introduce myself. So I'm called Serge Lodo. So I'm working for Renault in Research and Development Division. And I'm specialist in power electronics, and I'm involved on all advanced engineering projects we can have in the field of power electronics. So that is for sure pure electric vehicles, hybrid vehicles, but also, and what I will talk to you today, about fuel cell vehicles, which is something that is coming from let's say, in the coming years on this decade. So I will talk about the high voltage electric architecture for fuel cell vehicles. And to introduce that, I will just remind you that Renault, first, we are a key player in battery electric vehicles. So we have actually, some top-selling vehicles like the new Megane, Zoe, which has been one of the leader of the sales up to last year, who has been overtaken by Tesla Model 3, Kwid, and also we have some hybrid, which is the Megane. Some other are in development, so we are going on in that way. So you have maybe seen this Renault 5. I don't know what will be its commercial name, and also this sport car Alpine, which are all electric, and of course many others are on project and will come, but of course I cannot display them today. So, of course, we are not alone. Many, I would say, all of our competitors are going in the same direction. So you have seen recently all the Hyundai Ioniq 5 and other Kia and so on the same platform, who is going on sale this year. Of course, Volkswagen, who is highly active, and the top selling of last year, Tesla, of course. You can have also Mitsubishi and Toyota. Of course, this is not exhaustive. You have a lot of other examples. Just notice that the EV is the most growing segment in the year 2021. We expect this trend will follow in the coming year. And of course, technically speaking, this is a huge change in the automotive industry, because all those cars have in common an electrified powertrain. That means electric motors and a lot of power electronics, and which is quite new. So you still have, for hybrid or plug-in hybrid like this one, combustion engine, but this is always living together with the electrified powertrain. So a big question, why this trend to powertrain electrification? Because this is mainly this represents a lot of constraints, technical, economical, and so on. So why? There are mainly 3 reasons. So the first of them is, I think you're aware of that, the CO2 reduction. Actually, transport and mainly automotive is responsible for almost 1/4 of all CO2 emission, which is quite a lot. And actually, in most part of the world, it doesn't go in the same speed everywhere, but there are a huge trend, many constraints that can be different. to reduce this CO2 emissions. So the first one is to say, okay, you have to reduce, let's say in 2021, this was 95 grams per kilogram and per car in average of the production. So that means each one of the car you are selling, you have to be below this this value. And if you exceed this value, you have strong penalties. Let's say 95 euro per grams and per vehicle sold. So for a big manufacturer like Renault, Volkswagen, Stellantis, and whatever, this each gram represents several hundreds of million euros per gram. So this is a very huge fee that we have to expect. And 95, which this is decreasing to go down to 59 in 2030, with the same penalties, you cannot achieve this without selling pure electric vehicles, which are zero emission, of course, by their use. So this is mainly in Europe. As I mentioned, Europe is a pioneer in this huge constraints in CO2 emission. But the same you can see the same trend in America, Japan, China, and later on in Asia as well. So that's it. A second way is the air quality. So we are not in CO2, but clearly in the regulation for pollution. And this is why we have to help the combustion engine with some other, let's say, electric assistance to make it fulfill the future Euro 7 regulation. So this severity that sharply increased compared to what actually we have Euro 6E, which is the actual normalization. For example, this one will have exactly the same emission tolerance between diesel and gasoline engines. So that means even if you want to keep, let's say, a standard combustion engine vehicle, you will need to have anyway some electric motors and power electronics inside the car to manage the emission of the combustion engine. So this is a huge constraint, which is right now we have to be really it's very close. And a third one, which is not the least one, this is clearly the access restriction. So you can see this. So this is just an example that we can have the Green Energy Transport and Environment in France, C40 cities, Clean Europe, and whatever, where locally they decide to have some diesel ban, combustion engine ban, and so on, to make because it's mainly social pressure or coming from media influencers, and basically population now is more and more aware of the disagreement brought by air pollution, and clearly they don't want it. That means some ban of combustion engines. So this is a map of where we are, the main city. You can see in Europe, Paris, Barcelona, Madrid, Milano, and so on. There are many others, but this is also something that is growing more and more. So as I mentioned, European Union is clearly a pioneer, but basically this is the main trend. Okay, so now just let's have a deeper look on the pure EV. So if you listen to what the customer requests today, it will say, okay, no problem to go with an EV, but I don't want to change any other things. So that means they will request more or less an autonomy of 400 to 500 kilometers. So this is for passenger vehicle. So what does that mean? That means a huge battery of something like 500 kilograms that, depending on vehicle size, would store from 70 to 100 kilowatts hour of energy. So you have a small picture here. So I think it's a Hyundai Ioniq. And you see more and more now we have a dedicated platform for electric vehicles, mainly to store this huge battery that you can see here. And you can see here also electric motor, power electronic, charger, and also rear powertrain electrified if needed. So this is in real life. You can see here a picture of what looks like such a battery. This is really huge. So more or less 300 liters, 500 kilograms. And by the way, the overall vehicle weighs between 1.5 tons up to more than 2 tons, which is quite huge. Acceptable for passenger vehicle because they don't really care about that. But clearly, this is a huge increase of weight of EV due to this requirement of autonomy. Also, what I want is availability of the car. So, of course, they request to charge more and more faster. So, basically, they require a fast charge from 20 to 80% of full energy in, let's say, 20 minutes, 25 minutes. This is what is seen as acceptable by a customer. So that means you need to have fast charging station, let's say with the power of 150 kilowatt up to 300 kilowatts. This is the order of magnitude. And to finish, okay, I mentioned this is acceptable for a passenger vehicle. But for commercial vehicles, where loading capability as well as volume capability is a key value, clearly this is not acceptable where battery is taking, battery weight is, it has to minimize the global loading weight you can have. So this is the first reason why where H2 fueled vehicle is an opportunity to this, because first of all, the charging time, so fueling, it's more or less fueling hydrogen, is clearly the same thing as fueling in time, at least as fueling with gasoline. And of course, storing hydrogen is very light, so you won't have this penalty of weight. Okay, so let's have a look of what is actually the fuel cell dynamics. So you can see actually this is a very niche market. You can see some passenger cars like Toyota Mirai, Hyundai Nexo, and so on, who are here, some passengers. So a high powerful fuel cell, let's say 100 kilowatts, sometimes more. A lot of stored hydrogen, 5 to 6 kilograms, and a small battery. Basically, this is because it's a niche market, so they don't invest so much in engineering fee. That means most of electrical parts are carryover from a hybrid device. That's true for Hyundai, Toyota, Honda as well. And you have two other aspects. The first one is what we call the EV range extender. So that means you have more or less, this is an EV car where you lighten the battery. So let's say around 40 to 50 kilowatts hours, so half of the battery, where you add a fuel cell vehicle, a fuel cell tank with a low power, let's say, which is able to deliver an average power that is consumed by the car. So in city or suburban traffic, basically you will have an average consumption of 5 to 10 kilowatts. That's it, not in peak. And this is an average on let's say, a few minutes. And a few quantity of hydrogen we stored. This is more or less 1 kilograms of hydrogen. So what we call this is an EV range extender. So this is clearly an EV where you have a small battery that fulfill, let's say, 70 or 80% of the mission profile you can have statistically. And for longer trip, which are statistically more or less 10 to 20% of the usage, you will start this small fuel cell. So that's a first design. And the second one, which we call mid-power utility vehicle. So this is more for bigger cars. So let's say for Renault, that would be something like a Kangoo here, and here a Traffic and Master. So you can see bigger, where the battery would be much smaller, let's say 20 kilowatts hour or less. You will store more hydrogen, so 3 to 4 kilograms, and a bigger fuel cell, because the request average power is much higher. Okay, so more and more the usage of the fuel cell will grow when you go that way. Okay, so this is a huge point, but there is something very important to notice is whatever you can have this balance. So it's mainly a customer approach. You will have two power sources that will have to live together. First of one, of course, is the battery. The second one is the fuel cell. And for this, you will have to have a specific power electronic device that control the power flow between those both power source. So, which is what we call DC to DC conversion, which is mandatory. So you need to have at least one of them to manage this power flow coming from two sources, those two sources. Of course, it has to be bidirectional for battery. You can charge or discharge it during a trip. For fuel cell, definitely, you can only discharge the fuel cell. Okay, so we have different possible electrical architecture depending on the size of battery and the fuel cell you have. The first one clearly is when you have something what we call EV range extender, small fuel cell. Basically, we are putting the DC-DC converter in the smallest power flow. So we can have something like this. So we carry over the overall fuel EV architecture. Well, we have this add-on here for the fuel cell. The DC to DC converter can also be a boost to the battery. So that can be more or less for when you have a bigger fuel cell and a smaller battery. So it can be for a mid-power range or a full power for fuel cell like a passenger vehicle. So, for example, the Hyundai Nexo is acting as it is. And by the end, it can be seen quite more heavy in terms of power electronics, but it helps a lot, is to add a DC-DC conversion below both DC source, so battery as well as power fuel cell. So this is clearly easy because you can manage the powertrain voltage, whatever is the one of the battery and the fuel cell. It helps to have a carryover, a reuse of what's existing in terms of powertrain component, battery chargers and whatever, regardless the sizing of the battery and the power electronics and the fuel cell, sorry. So this is why mainly Japanese fuel cell powered cars are using this kind of architecture. Typically, this is the Toyota Mirai and Honda Clarity. Okay. So right now, how do they look like? So typically, the DC to DC converter is made as it is here. So a Q level, so that contains a single layer of transistors with a passive filter, in general an inductor, that converts the low voltage source, let's say a battery or a fuel cell, into high voltage that supplies all the electric powertrain. So this is a basic scheme. After, you can have multiple cells like this in parallel, of course. But also, you can have some other ways to work. For example, a free-level T-type clamp. So let's say with a short circuit at the middle, at the midpoint, that can help to have a free level, what I will show you in the next slide. And also with flying capacitors. So let's say you have a single cell leg. Here you have this one, which is imbricated in a second switching cell like it is. So having a free level is interesting mainly when you have a high voltage powertrain here. So as you know, more and more we are moving from here for the powertrain from 400 volts, let's say around 400 volts, up to 800 volt supply. So it has some advantages and disadvantages, but for high power powertrain, it's more advantages. So that's why we can see coming, the first one was the Porsche Taycan, electric Porsche, because it has a huge power and they want to have a very fast charger. To be able to do that, they have a big battery and a high voltage to limit as much as possible the current. But now we can see a huge trend in that way. So all the Hyundai Kia cars are in 800 volts. Some other Germans are coming on that way. Let's say Stellantis as a platform that will be in 800 volts. So this is a huge trend where Q-level DC to DC converter would be a real advantage. And after that, I would say there's some key values for power electronics in fuel cell. This is true as well for hybrid and as well as for pure EV. But this is really more valuable in fuel cell. This is efficiency, because those DC to DC are in series with other conversion stage. So we need clearly to have the highest efficiency to have to don't minimize, reduce significantly the overall efficiency of the electric powertrain. And by the end, the compactness, because if we reduce significantly the weight of the car by using a fuel cell, you will have a lot of volume due to the energy hydrogen storage. And this is, in terms of architecture, very hard to manage. And of course, electronic function is a key player to help to have the highest compactness for helping having something realistic in terms of architecture. So those key values are right for any electrified car, but mainly for fuel cell powered cars. So now let's have a look of how it works. So as I think you know, this power electronics, so if you look to a single cell, it will work in PWM, pulse-width modulation, where the average delivered voltage, so the ratio between high voltage and this V load, will depend on the duty cycle you apply. So here you have this average value, and here this one. So the duty cycle helps to control what is the output voltage. If you have a free level converter, so let's say something like a flying capacitor or T-type clamp one. Here I shown you for a 800 volt network. So on high voltage, you can see what is the output voltage, the load voltage here, depending on the duty cycle. So when you height at 0.5, so you change from the 400, 0 to 400 pulse to 400 up to 800 volts. So this has a huge impact on filtering stage you can have here, because you can significantly reduce this filter size by dividing by 2 the amplitude of the pulse, and also you have an apparent frequency that is double than a two-level one, because of course both are 180 degrees shifted, both legs at 150 degrees shifted. So what does that mean? So you have half of the amplitude, and also the first switching harmonic is twice the switching frequency. So that means you can lower a lot the passive element, first the size, and also the volume. So that helps a lot for capacity. But in another way, it helps also a lot to control the power flow dynamics, because of course you reduce the inertia of this filter. So what is usually how it works? So of course the goal is to control the current or power flow or whatever by controlling the low voltage current. So this is this. So you have the load. I put it here, a load. It can be a generator, of course, if this is a boost converter, for example, a battery or for a fuel cell that supply the high voltage. And to manage this, you will have to control this voltage. So basically, you can have the first way corrector parameters, sorry, here. So just this control here should be enough, but very slow. What we expect generally is to have here a measurement of the output. So basically, we know what is the voltage of the battery or the fuel cell. So what we are adding is clearly a feed-forward, so a direct open loop control that will provide most of, let's say, 80% of the reference load. That will help to have a more and more dynamic correction stage, just to adjust what are the error. But most of the duty cycles will come from this open loop, let's say high voltage divided by this measured low voltage. Of course, you can have some better tuning by using the current measure if you have an idea of what are the impedance and whatever. But usually this feed-forward control here is fully mandatory to help to have the highest control dynamics. Of course, this corrector is generally quite simple. So in most of the case, it's clearly proportional integral, but more and more, it's better to have something a bit more complex, stable, and dynamic. But this is this. And at the end, you have to manage this to have the great modulation strategy to work and to apply the right pulse on the converter. So that can be single stage, so it helps if you can have some parallel one with different filters or integrated filters, or a multi-stage, basically two-stage. So in any case, you will have in general more than two switch to control compared of what we can see here. So this is a classic scheme. Basically, you have at least 4 cells to control, and sometimes more. Okay. And from a technology point of view, so we can see, as I repeat what I told a few minutes ago, for power electronics, key values are clearly compactness and efficiency. So that means the use of wideband gap semiconductors is clearly mandatory, at least for fuel cell vehicles, but it will go also, it's a huge trend for pure electric vehicles, to be best in class in those 2 criteria. So just to remind you, wideband gap semiconductors, that means usually we are using for semiconductors, even for power electronics, silicon as the basic material. So it works very well, of course, but the trade-off is what we call its band gap. So the energy necessary to extract an electron for valence energy to conduction path. It's quite low for silicon, which is 1.1 eV. And the goal is to move to other material. There are 2 main ones. The first is silicon carbide. So just in the crystal, you add carbon in the silicon. So this is quite tricky to do because there are many crystalline possibilities, and there's just one which is what we call 4H, who is able to deliver a good electron band gap. So that will go up to 3.4 3.4 EV, so it is 3 times higher than the silicon. What does that mean? That means for a same power and same blocking voltage, you will be able to have electric field which are, let's say, 10 times higher in the material without breaking it. So that means you will have a concentration of dopant, let's say 10 to 100 times higher than what we have in silicon. And by the way, reducing its own resistance by significantly factor, let's say 5 here. So I just mentioned here, you can see what's the best one actually, what we have with superjunction MOSFET. So this is the high-speed MOSFET made in silicon, where we have a standardized own resistance, which is around 20 million centimeters square for a 650 volt device. With the silicon carbide MOSFET, we are clearly at 4 million centimeters square. So you can see for the same current, you can reduce by 4 to 5 the area of the component. So this is clearly significant. A second material that is usually used and will be more and more used is the gallium nitride. Okay, so this is today, this is highly used in opto for all the LED you can have everywhere to light are made with GaN, but it can also be used for power. In that case, we are using what we call a HEMT, which will high electron mobility transistor, which is a lateral one. So you have the drain and source who are on the same layer, in the opposite of the MOSFET, where the drain or source are on that way, on the vertical way. So this is on the lateral way. The GaN has a bit higher band gap, which is 3.66 EV. And also we can use it by what we call HEMT. So it's on the what we call 3-5 components. You add a 2-layer interface with GaN and here AlGaN with the addition of aluminum make a bit higher band gap that makes the interface, you will have theoretically a quantum well. That means you have 3 electrons that are able to go when you have only a few electric fields. So this is very high frequency component. Basically, so this is a trend to use them in high frequency conversion stage. Today, mainly onboard chargers and also DC to DC converter, at least when you have a transformer from high voltage network, than to supply the 14 volt accessory network. But that can be also studied for high power DC-DC conversion that I told to you. And to finish, we can have, but this is clearly actually still in academic research, but huge potential to use this material again for vertical structures. So you can see here some different one, but basically, even if they own specific on resistance very low, it doesn't exist yet. Here, all those 3 first components here can be sourced on the market, on different manufacturer. So just to remind, if this this wideband gap component is a huge trend to be used in power electronics for electrified car, there will be more or less mandatory for fuel cell propelled car. And just remind, for those key value, the efficiency will mainly come from their very low on resistance, so that generates less losses. And the high electron velocity allowed by, first of all, the electron mobility of the material, which is not so good for silicon carbide, quite better for GaN. But due to the high frequency field you can have in both material, the electron velocity is very much higher than in silicon, and that allows higher switching frequency. That allows better compactness, because higher switching frequency, as I mentioned, means much lower filter size, and by the way, more compact conversion stage. To finish, I would say, just to remind to you the four main takeaways for this. The first is that a fuel cell vehicle clearly is a niche market today, but which is expected to grow during this decade. Mainly in Europe, but not only. You know, there are a lot of wish by the EU to push hydrogen as a new energy for industry, but as well for transportation. So fuel cell will have a huge a key role in that. But also this trend is right in Japan, China, and also North America. For the electrical architecture, you will have to remind that two energy sources must be managed, which are highly different, and this implies additional DC to DC conversion. To finish, H2 storage and fuel cell efficiency. So the two key values for power electronics and globally for the overall the car, but mainly for power electronics, is efficiency and compactness. Of course, to be put in balance with the cost. This is an evidence, but of course, we have to sell the car. And to finish, this implies technology breakthrough. So, while at least while using wideband gap components and also high frequency, very tricky control law, because this high frequency will have to use a very low period of calculation for embedded processor and so on. So that's it. And this, to finish, even if it's a niche market, this technology improvement due to specificities of fuel cell vehicle will help to develop as well for pure EV or hybrid vehicle, where it's more massive deployment, and we can have more, let's say, take more technical risk for that niche market today. So that's it. I would say thank you for listening to me, and ask me any question you want.
Thanks a lot for your presentation. Do you have any question? As usual, you can ask them directly.
Hello.
Hello, yes.
Yeah, this is Sagar here. I would like to ask you something. Yeah. So, like, there was a slide where you compared all the three different architectures.
Yes.
Yeah. So, in that, when the car, even after combining two architectures, the car will have a particular range. Yeah. No, the previous one. Yeah.
Sorry, this one or this one?
Yeah, this one. Yes.
Yes.
So, if I consider it for a vehicle to be a utility vehicle, and for a utility vehicle, if two powertrains are combined, it will have a particular range. So, after the car gets discharged, like the battery and the hydrogen gas is almost on the verge of getting over, it will be required to refuel. So, all the charging stations will also have to be equipped with the refilling of hydrogen and the charging of battery.
Yes.
So when the refueling will be done, both things could be done simultaneously, or the first the battery has to be charged and then the fuel has to be charged, or how will it work?
Yes, I understand. So you have to manage, it depends. Basically, for this application, you will have, it's mainly an electric vehicle. So basically, you will start your trip on the battery, and if it's a bit longer than expected, let's say when you are lower than 40% of state of charge in the battery, you will turn on the fuel cell, but the fuel cell will be used statistically quite 20 to 30% of the time. So of course, most of the time it will be an electric vehicle that you have to plug on the network. On that way, in general, it's some hybrid cars. So sometimes you don't have any battery charger in that case. For example, Toyota Mirai have no battery chargers because it's a very small battery. So it's a pure fuel cell. When you key on, you start the fuel cell, so it heats up and has a lot of way to work. And all the power comes from the fuel cell. The battery is only here as you have for a hybrid. To sustain to help the fuel cell for power flow huge variations, because the control of your fuel cell, you have to fuel in with hydrogen, and the dynamics is around 1 to 2 seconds, so which is quite too long compared to what's expected by a driver. So the battery is here to bring the huge variation compared to the average. And for this mid-power utility vehicles, we will have to manage a specific power flow. So I think, frankly speaking, this is something we are thinking about in the design. We will certainly ask to the driver to say, what do you expect? And also we will need to have some specific algorithm to manage the power flow between fuel cell and battery. So typically, of course, if here we can have some short range, let's say a trip only with battery. This will be the case, for example, in some city where you ban anything, and sometimes even a fuel cell won't be possible. So that will be more or less the way of working as you have with the plug-in hybrid. For example, Mitsubishi Outlander. So with a small battery, so where you have, let's say, a few tens of kilometers of autonomy on the battery, and rest of the trip is the energy is done by the fuel cell. So, okay, so I think the driver will have some action, but basically we will have huge management, and fuel cell will be on most of the time. So that's it. And of course, you will have to manage two, let's say, tank, hydrogen, and battery state of charge. So the energy management, depending on the strategy, will be really different. Let's say most of the novelties will be here. Here, this is clearly an EV range extender. So the driver will say, okay, I push the button, I want to be helped by the fuel cell, or the vehicle will decide by itself to start the fuel cell if the battery state of charge grow below a given state. Here, fuel cell is always on, so this is the battery management, more or less like an hybrid. And here you can compare it to a plug-in hybrid, which is of course, the energy management will be the most complex.
Okay, got it. And one more thing, like suppose during the driving condition, if there is a condition that more torque is required, in that case, can two of the modes, fuel cell and the battery, can supply parallelly like a parallel hybrid mode to drive the motor?
Excuse me, I'm not sure to have understood your question. You mean when we have both,
Yeah.
to have, let's say, a boost in power if needed?
Yes.
Yes, this can be the case. I would say that would be a cherry on the cake for a passenger vehicle, for example, depending if they want an additional power. That is more mandatory for utility vehicles. Let's say, for example, a full loaded car that is growing on a mountain, and that will request a huge power. And in that case, yes, we have to be clear and to anticipate it by using both power, because as you know, for example, for passenger car, whatever they come from, you have a lot of derating. So you can be hours and hours at full throttle, because for heat up of engine and so on. And you know, for whatever car, if you test on the notch life of a Nürburgring, except Porsche, but you have to pay for this, all after a few minutes are in derating. And for a utility vehicle, this is not acceptable, not for performance, but only because you have to be to climb some mountains at full load, and that request an average power which is quite high compared what you can have usually. So clearly, yes, this is something which is requested, and we have also huge impact, because in many cases say, okay, we'll carry over a powertrain from an electric vehicle. And for utility vehicle, in some cases, the average power on a cycle is too high, and you have some derating. So basically, definitely, yes, we have to have both power to boost, and sometimes for a long time, because the customer clearly needs a huge average power.
Okay. Then when you burn 1 kg of fuel cell of hydrogen, a different amount of energy in kilowatt is produced. And when you use 1 kilowatt of battery, different energy is produced. So how would you balance the torque if two energy sources will be producing different amount of energies?
Excuse me,
Yes.
has been some echoes. I'm not sure to have understood.
Can you hear me now?
Yes, yes, yes.
Yeah. So how would this torque balancing would be done by energy produced by two different sources on the same motor? Yes.
Also, yes, please go on.
Yes, you would require a DC-DC converter from which energy would be produced from fuel cell. And another DC-DC converter would be converting energy from the battery. So how would this torque balancing would be done on the same motor where two energy sources are supplying power?
Yes, so maybe just on that slide, you can see that here, so depending on where we are, so you can see here, this is the battery is fixing the voltage of the powertrain. So the electric motor also will see the voltage of the battery. So when you push the throttle, you will request via the inverter a current, and this current will be displayed by the battery, or if you accept to control, the DC-DC will flow some current as well, and to help the battery. Even you can charge the battery with the fuel cell. For example, if you are stopped at a traffic light or whatever, can have the fuel cell deliver the current in the battery. So you can have ATCs. So here, of course, you can have the same function, but the DC-DC is controlling the power flow of the battery. But basically, this is the same. Here, when you request some torque or power, you know what will be the current, and you can, by a supervision of the vehicle, control simultaneously the torque request on the electric motor, on the inverter, as well as the current flow or the power flow from the DC to DC. So at each time, this is done by, let's say, high-speed CAN. So generally, the period of refreshing those orders are at 10 milliseconds. So for human level, this is quite fast. And at each time, 10 milliseconds is significantly enough with the control dynamics we can have to have a steady state situation for the power flow. So of course you have both control simultaneously via supervision of torque of the motor and DC to DC converter. So it's one, it can be control the fuel cell power or the battery power. But in any case, of course, both have to be balanced. And I would say the most critical one is here, because to be sure that there will be no unbalance here, because every power flow are controlled by a converter, DC to DC for fuel cell and high voltage batteries. And by the end, also the torque by the inverter. So in general, you apply here, so it's a capacitor bank you can have here, and the DC voltage is controlled, and the supervision adds some correcting power flow to manage and to say, okay, to be sure that in real life, the power flow is balanced, okay? Because in that case, the voltage would increase or decrease quite fast if all would be in open loop. So typically in that case, yes, in the supervisor, you will need to have a specific loop that corrects the power flow to manage a required voltage distributed on all high voltage network. In that case, it's quite simpler because it's fixed by the battery or the fuel cell. But anyway, yes, you are fully right. There are two levels of control. One is the very high speed with controller at the converter power conversion stage. Let's say DC to DC or inverter or whatever. Well, they apply a request. So here a power flow, here a torque. And you have a supervision stage that controls everything, the state of charge, the control of the hydrogen feeding of the fuel cell and so on, the torque of the electric motor. And also in that case, it will have to control its more slow regulation, lower dynamics, but you're sure, for sure, you will have to control this voltage to be sure that all the power flow in reality are balanced. I don't know if this answers your question.
Sure. Thank you.
I have a question.
Yes.
In the first case on top, where it looks like the DC-DC converter is connected to the fuel cell, what then happens to taking care of the dynamics of the HV battery in terms of, let's say, when there is an acceleration or something, the power flow from the battery, doesn't it affect like the voltage dips and those things?
Yes, so you're fully right. So let's say this is something that is managed also by the supervision. So of course, basically the battery is designed here to sustain the power flow, so very high peak current in some case and some regenerative power when you leave the throttle. And of course, in some case, for any reason, the battery management will say, in general, it's a thermal limitation. Okay. That will have some derating. And in that case, the derating is managed by the overall supervision. Basically, the main aspect is that it will derate the power of the traction motor. Okay, so that means instead of having a peak power of 150 kilowatts, for example, okay, if the battery becomes more and more hot or for any other reason of derating, you will have a small derating in power. So at the same pressure of the throttle, you will decrease to 150, 140, 130 kilowatts. So smoothly because we don't want to be the driver mustn't be surprised to have a lack of power, but basically this is the case what happens. So it can happen for the battery, but also for the cooling of the electric motor or whatever. In that kind of car, you have many measures that are managed and that can be a cause of derating in power.
So in looking at the derating in power and then looking at all three architectures, which one would be the best economical choice? Because derating seems like you have your motor and you lose.
There is clearly no best choice. It's highly linked to what's the balance you will have to choose here. Okay. If it's so sorry to have no basically if you have here, this is what is doing. You say here we can have, this is clearly a carryover of what we can have for a pure EV. So let's say we remove some battery packs and we add a few fuel cell system. So to be as less intrusive as possible, we keep all those elements with the derating in the battery and just adding fuel cell system, hydrogen storage, and DC to DC converter. So economically, it makes sense because actually the expected sales is quite low. And so you can sell quite fast, very fast time to market a car or mainly a utility vehicle without changing so many things. So this is the case. Renault is selling Renault Trafic. Let's say the design has been done in 1 year. Stellantis is doing something quite very close. I know that Volkswagen is looking at it. So, but as you can see, what I know for Renault, this part of the propulsion is put on the hood of the car. And so that's it. And we kept the pure electric traffic that was on sale right now. So economically, that's it. The most advanced, I would say, you can see for this technology is the Toyota Mirai, because they are at their second version. You know, they sold first Toyota Mirai 8 years ago, I would say, which was more or less a carryover of elements of hybrid Toyota Camry. This is you can see if you go to New York, most of the taxi drivers have a Toyota Camry. And those elements with additional DC to DC converter, of course, the fuel cell. The second version of Camry is more optimized, and we can see that they have invested more in technology specifically for fuel cell vehicle. For example, all the power electronics are in silicon carbide, which is the first Toyota car, which is 100% silicon carbide. So that's it. But thing that I would say the best economic balance today is more or less the smallest engineering effort, because expected sales are very low. So this is a trend. But in the coming years and by the end of the decade, we can expect to have some additional engineering and R&D effort dedicated to fuel cell, because we will have a growing market. So that's why it's interesting to see what Toyota has done, because it was a pioneer in that field, and is the first to have make some real efforts to develop a specific technology for fuel cell. For all the others, this is more or less a carryover and manage at minimum engineering effort, because this is the most optimized economical way for a project. But clearly that the picture of today, and we can expect more and more specific design and optimization where the sales will increase.
Okay, thank you.
You're welcome.
We still have a bit of time, so if you have more questions, feel free. There is a question on the YouTube. I'm not sure you answered it already. What type of DC-DC boost converter structure is used for Renault EVs?
So actually for EV, we don't have boost converters. For fuel cell vehicle, well, on this type of structure, so it's, let's say, a range extender. So actually we only have a fuel cell car, which is a utility car. So this is that way. And for the DC to DC converter, this is today a two-stage converter, which is quite basic. We expect for next generation, maybe it will go higher in voltage, and we'll have to develop and optimize this. But today, DC to DC conversion is quite at the most usual way, because the biggest constraint was the time to market.
Do you have any other question?
Hello.
Yes, hello.
Thank you for the talk. I want to ask, talking about the following years, in your opinion, what are the main areas of opportunity for our generation as electromobility engineers to work on in the following years, as you mentioned before? But in your opinion, what are the area or opportunity?
You mean of technology or energy?
Yes, I mean, in terms to be more available, this technology of fuel cell.
On technology of fuel cell. Okay.
Yeah.
I think today clearly the main trend, and in my opinion, for the coming year, that will be the PMFC, proton exchange membrane fuel cell, because today this is clearly the most efficient fuel cell we can have, and in terms of efficiency and capacity, we don't see something better to come in the coming years. But anyway, for some application, we'll have to look what we call the hot fuel cell. So let's say that fuel cell that works at much higher temperature, where we can expect better efficiency. That would be certainly for a specific mission profile where those fuel cells are used most of the time, and not only like passenger car where 96% of their life they remain parked. So this is something that could be a kind of evolution. But today, keep in mind that clearly the main trends for the coming years will be the PEM, proton exchange membrane fuel cell. Today, we don't see something better. Just to add, there are also a lot of work, R&D done to produce hydrogen, so electrolyzer and so on. And that could help also development of some new generation of fuel cell, because this kind of propulsion fuel cell makes sense only if you use what we call green hydrogen. So that means hydrogen carbon free,
renewable.
Of course. And to produce it today, efficiency are not so good and so on. So there are a lot of R&D in that field, and that could help to accelerate also development of new structure of embedded fuel cells. But let's say for 5 to maybe longer years to come, proton exchange membrane will remain the king.
Okay, thank you very much.
You have any other question to ask? Okay, then thanks for joining and for your presentation.
You're welcome.
It's always a pleasure to have you every year. So we'll contact you again next year. So around next talk will be in 15 minutes, but it won't be broadcasted live or recorded. So we can do a short break with the students, and we connect again in 10 minutes.
Okay, good.
Thank you very much again, and
Thank
I
you.
wish you a great day.